That's why I have no work method.
So, just walking through it. Use your division here to simplify each piece. Subtraction of your exponents here, those cancel here, and just rewriting it here. Antiderivative of this guy is that guy. Considering the derivative of x is just 1, there's nothing to consider. Antiderivative of a constant, just 2x here. We have to consider the -1. We don't have a -1, so we have to multiply by it. And then I just rewrote it to be a little more simple. So for this one, if the function that I'm looking at is my e3 to the x, so if I were to do u substitution here, I would say my u would be 3 over x. Rewrite that as, or 3x to the -1. So du is going to be -3x to the -2, or -3 over x squared. We have the over x squared. We don't have the -3, right? So we're going to have to do that multiplication by that -3 there. And so my final answer for my antiderivative is just going to be this function times your -3. So you have -3 e to the 3 over x as my antiderivative. And we're taking it from 1 to 3. And so we have -3 e to the first power, 3 over 3, right? Minus -3 e to the third power, 3 over 1. You're right. There we go. We divide out the 3, sorry. You have a -3, you don't want it, so you have to divide by the 3. All right, does that make sense?
So purple to red part.
Okay, so I didn't write the whole u substitution. So with u substitution, you are trying to get it to look just like this. When I take the derivative, so u is just my exponent. When I take the derivative, I get -3x to the -1, or -3 over x. I don't want it, so that's why I divide, sorry, not multiply, by the -3. So if I were to rewrite this, this would look like -1/3 e to the u du, right? The antiderivative of e to the u is just e to the u. So you get e to the u, and then replace your u back in here. So that's how I got -1/3 e to the 3 over x as my antiderivative. And then you just plug in your numbers, 3 and 1. So anytime you have an e to the something over x, and then you have something on the bottom that's an x, you're going to use a u substitution there. All right, so the first thing they do is they define it for us here. If a is a positive real number, not equal to 1, and x is any real number, then the exponential function to the base a is denoted by a to the x and is defined by a to the x equals e to the ln a of x. All right. The reason this works out is because your e and your natural log cancel, and then you just have a to the x. So they write it that way because that's how the proof works. All right, these functions obey the normal laws. Anything, doesn't matter what base it is, taken to the 0 power is going to be 1. Any base divided by that same base, you subtract their exponents. Any base, when you multiply, you add their exponents. And a power to a power, you multiply. That should be very much review from like Algebra 1. The most common use of exponential functions is radioactive half-life when you look at like scientific examples. In fact, in pre-calculus, we did a half-life with Chernobyl, if you remember that long ago, all right? So it says the half-life of carbon-14 is about 5,730 years. If 1 gram of carbon-14 is present in a sample, how much will be present in 10,000 years? And so anytime you have a carbon or like a half-life, your function is always going to be an exponential. Half being your base, how many years divided by your half-life years, 5730. This is what half-life formulas always look like. They are always exponential formulas. All right. And they said, notice that when you reduce it by the exact number of years, you have half of a gram. That's what half-life means. After that many years, you'll have half as much as you started with. All right, so it says when when time is 10,000 years is what we're looking for, 10,000 years. And so you would simply do the 1/2, 10,000 years over the 5730. And you have approximately 0.3 grams left. So this is what half-life, this is what you're used to with exponential functions, right? And they use exponential functions for all types of growth, but they also use it for decay. Decay being, what you'll notice with decay versus growth is that your exponent is going to be a decimal, time over 5,370, versus growth would be like to a rate, number of years would be growing there. So if your base is going to be a fraction, you'll have decay. If your base is going to be something like investment, where it's not a fraction, you'll have growth. All right. They start talking a little bit about logarithms. And this is basically your change of base formula. They just wrote it a little bit differently. Change of base formula, when we looked at it back in pre-cal, if we had log base a of x, and obviously on your calculators you do not have log base a, b, c, or d. You have log base 10, which is log, and you have log base e, which is ln, natural log. Your change of base formula says that you can do the natural log of your number over the natural log of your original base. They've just written it differently, but it is the same change of base formula. So that's one of them. Base a is defined that way. Base a is defined as your natural log of that number divided by your natural log of the base you're trying to find. And you can convert between bases. And think about your base as just your base of the exponent. If your 2 is your base, you're saying 2 to what power equals this x. That's what logs are. It's the inverse of your exponential function. These properties are ones that you should be familiar with as well. Y equals a to the x if x equals log base a of y. Your log is your inverse of your exponent. A base a as an exponent will cancel out a base a as a log. So a to the log a cancels each other out. You're left with just that x. Same is true here. Log base a of exponential base a also cancels each other out, and you're left with just x. So bases cancel out bases. Like bases cancel out like bases. And then they give you some examples of that. All right. Solve for x. There's actually 2 ways to solve this, all right? And I'm going to show you both ways because if you come upon these in some other world, like a standardized test or in college or something, I don't want you to go all the way back to change a base always. So the first way you could do this is change a base. If I have a base 3, then I can cancel out that base 3 with a log base 3. So log base 3 of both sides here. All right. Now, in order to use this particular method, you have to recognize that 81 is a multiple of 3. All right. It is going to be a base 3 number. All right. I can take 3 to a number and get 1 over 81. So on the left-hand side, my log base 3 cancels and I'm left with just x. All right. On the right-hand side, I need to rewrite this 1 over 81 with a base 3. So I have log base 3. And it's 3 to the negative 4, right? 3 to the 4th would be 81. So 3 to the negative 4 would be 1 over 81. So you have to recognize that to use this particular method. You have to be able to recognize you have a like base. If you notice that, then you will be able to cancel out this base on the right-hand side as well, and you will get just x equals negative 4. So that's one way. You can also take the natural log of both sides, by the way. You'll have to use your calculator to do natural log. So if you're doing it without a calculator, you definitely want to look for bases that will cancel each other out. If not, you can do natural log of both sides and expand and just divide by that natural log of 3. But it will equal negative 4 no matter what you do. All right, on the right-hand side, this is a base 2. I want to get my log out of my problem. So I'm going to do an exponential base 2. All right, so I'll say 2 to the log base 2 of x equals 2 to the negative 4. And when you do that, your bases cancel out. You get x. 2 to the negative 4 is just 1 over 2 to the 4th, which is just 1 over 16. So the right-hand side, you don't even have to recognize anything other than that you have a base 2. On the left-hand side, you do need to know that 81 is a base 3 number. All right, so let's try a few of these. Expand this guy right here. Once you do natural log of both sides, I can pull the 2x in the front to natural log of 3 equals natural log of 75. And then I can divide both sides by that 2 ln of 3, 2 ln of 3. So x is going to equal ln of 75 divided by 2 ln of 3. That should be your answer there. If you did it using base 3, if I were to just take this guy and do log base 3 of both sides, right? On the left-hand side, my 3's and base 3's would cancel. I get 2x equals log base 3 of 75, and you have to use change of base formula there, which is natural log of 75 divided by natural log of 3 divided by 2. So you get the same exact thing when you do that as well. You just have to remember your change of base formula. So top of page 353, it starts to define your derivatives of your bases other than e. And I will say, this actually works for e. It's just that your e's cancel out. So if I were to go back to my derivative then of e to the x, let's see how this works. It would be natural log of e times e to the x. What's natural log of e? E to what power equals e? 1. So this actually cancels out to 1, and I get just e. So e to the x actually follows the same rule. It's just there's no need to write natural log of e because the natural log of e is just 1. Okay? So remember, base will cancel base, so it would just be 1. So this follows the same rule, except we no longer have base e, and so it's a little bit different. We don't have base e here, so we have to consider the base itself. So if I'm taking the derivative of a to the x, it is still going to be a to the x, just like the derivative of e to the x is e to the x. But I then have to multiply it by the natural log of a. All right? So the derivative of some base to the x is going to be natural log of that base times my function that they gave me to begin with, a to the x. All right? Right across from it, same thing here. I now have a to some function, a to the x squared or something like that, a to the 2x. I have to, in this one, consider my natural log of my base, my original function they gave me, and the derivative of my exponent. All right, so it's almost like chain rule here. All right, so if I just have a to a power, natural log of that number times the function that they gave me. If it is taken to a power other than x, x squared, 2x, 3x minus 1, whatever it is, I have to also multiply it by the derivative of the exponent itself. All right, let's look at derivatives of logs with something other than base e. So log base a, remember it would have been 1 over that, right? 1 over that, because vice versa for antiderivatives. Now I have to do 1 over that function times the natural log of the base. If I have base a of some function, it's going to be my 1 over that function times the natural log of a, and then also consider the derivative of the function. And they give the proof here. If you rewrote this a to the x as e to the natural log of ax, your e's cancel. So it's actually the same function as it would be with your e, except your e's cancel with your natural log, so you didn't have to deal with it when you had e's. So let's do some easier than it looks, I promise. They want us to differentiate these 3 functions. Differentiate these 3 functions, all right? The first one is just a base to a power, a base to a power. So if I'm looking for the derivative of this, it is going to be the natural log of my base, ln of 2, times the function they gave me to begin with, 2x. That would be my derivative, natural log of the base times the function itself. For the next one, I still have a base other than e here, right? Base 2. So I'm going to say natural log of 2 times the original function that they gave me, 2 to the 3x. Then I have to multiply it by the derivative of that exponent. What's the derivative of 3x? Derivative of 3x is 3. all right? So I end up with, these are actually my constants. These are constants here. 3 natural log of 2 times 2 to the 3x. And they did it with parentheses. That would be my derivative there. All right. So far, so good. All right, look at the last one. For the last one, I have a log base 10. So we're going to go up to number 4 on that page of bases other than e. We're taking the derivative of a log now. So it's going to be 1 over the natural log of my base, which was 10, times the function itself, right? Cosine of x. And then I have to multiply that by the derivative of this function. What is the derivative of cosine? Derivative of cosine. Negative sine of x. All right, so that's what I'm doing. 1 over the natural log of my base times my original function, and all of that times the derivative of my function, negative sine of x. Well, we can simplify this a little bit more. All right, so if I'm going to put this, I'm just going to go ahead and multiply it. Negative sine of x over natural log of 10 cosine of x. Sine of x over cosine of x can simplify. What is the sine of x over the cosine of x? Tangent. So this is negative 1 over the natural log of 10 times the tangent of x. That would be my derivative there. All right, when we're integrating bases other than e, remember if I integrate e to the x, it's just e to the x, right? So derivative of e to the x is e to the x. Antiderivative of e to the x is e to the x. So a to the x, or any other base to the x, is also going to be that base to the x, but I have to consider my natural log of the base. So integrating here is 1 over natural log of your base times your function, and don't forget it's plus c if it is indefinite. So for this one, my base is 2. So my antiderivative is going to be 1 over natural log of 2. And I'm going to multiply that by my function that they gave me to begin with, 2 to the x plus c. That's my antiderivative. Power rule. Power rule. This is jumping back to derivatives here. If you're taking the derivative, comparing these things, you have to consider your power rule. For example, on this first one, if I'm just looking at this, I am automatically going to think, oh, I have some variable involved. But e to the e is a number to a number, right? This would be like saying the derivative of 2 squared. That's just the derivative of 4. What's the derivative of any number? Derivative of any number is just 0. There we go. That's why we have that, all right? Then we move to our derivative e to the x. This is what we've been studying. The derivative of e to the x is just e to the x. I don't have to worry about a power rule here because my x is my variable there. But look at the difference between b and c. C is x to the e. E is a number, all right? My variable is now in my base position. I go all the way back. I would treat this just like if it were x cubed. If it were x cubed, my derivative would be x to the 3 minus 1, and I would be multiplying by that 3, right? So the derivative of x cubed would be 3x squared, right? Same thing happens here. I multiply by my exponent, e, and then I subtract 1 from my exponent, e minus 1. So you have to really start considering that e is a number. E is a number. All right, look at this last one. This last one, you're going to have to use your logarithmic expansion process. So this is the last one, and this is the most difficult one of these 4 here. All right, so let's look at this one together. We have y equals x to the x. So x to the x is not a number. E to the e was a number because it's just like 2 squared, 2 to the second power, right? X to the x, those are both variables. And so you do have to use your logarithm here. So you would take the natural log of both sides to expand this. Natural log of y, and you would expand that to the front. X times the natural log of x, right? And then to take this derivative, you're going to have to say, well, the derivative of a natural log is just the derivative of the function over that function, y prime over y. And then I would have to use product rule here. Derivative of the first one, that would just be 1. Derivative of this is just 1. Times the second, times natural log of x, plus the first, x, times the derivative of the second. Derivative of natural log of x is 1 over x. And so this would simplify to just ln of x plus 1. But that's what y prime over y equals. I need y prime by itself. So I'm going to multiply both sides here by y. On the left-hand side, rather simply, those cancel. Y prime equals this guy times y. And so I have to go all the way back to what my original y was, right here, x to the x power, right? So I would get x to the x power times the natural log of x plus 1. That would be my derivative here. So the first one, you're literally just going to take that first rule on page 353, I think, and natural log of 4 times your function. The second one, you're going to have to do the natural log of both sides. So you're going to want to do natural log of y equals natural log of x to the 2 over x. This will allow you to expand it. Natural log of y equals 2 over x times natural log of x. And then you'll be able to take the derivative. The derivative over here is just y prime over y. This you're going to have to use product rule. So think of 2 over x as 2x to the negative 1. That'll help you with your derivative. So derivative of the first is negative 2x to the negative 2 times the second ln of x plus the first, we'll just say x to the 2x to the negative 1 times the derivative of the second, which is 1 over x, or 1 over x is x to the negative 1.
Right, you don't.
So if I were to simplify this first, which is probably what I would do here, I'm going to actually go ahead and make this. What can I do there? Y prime over y equals negative 2x to the negative 2 ln of x plus 2x to the negative 2, right? So they're actually both, if I were to rewrite this, I could say this is ln, we'll say negative ln of x, negative 2 ln of x over x squared plus 2 over x squared, right? I still have to multiply, though, both sides by this y. So I also have to multiply that by my original function, x to the 2 over x. X to the 2 over x. So I do have to multiply by that. And honestly, I don't know if there's a nice, pretty way to simplify this other than these have common denominators. So you could say 2 minus 2 ln of x over x squared times x to the 2 over x. You could potentially simplify these guys by subtracting, but I don't know that it's going to make it any prettier. They simplified it a little bit more than that with your x's, but I don't know that it's going to. I'll show you what they did, so if you look in the back of the book and see the answer, you'll know what they did. So basically, we left the 2 minus 2 ln of x as our numerator, and we simplified these because they have like bases. So you basically have x to the 2 over x squared, right? So my rule says to subtract these two, right? So I would say 2 over x minus 2, right? Make sense? I have to get a common denominator here. So this becomes 2x over x, right? This is going to be a bigger number, so it actually ends up on bottom. And so they reversed it. So they have 2x, I think they do something like this, 2x minus 2 over x and put it on bottom. But that just ends up being your denominator to the 2x minus 2 over x. I don't know that that's any simpler than just leaving it multiplied out there, but that's how your answer in the back of the book would likely look if you did that. They just simplified their x's.